As I was recording this lecture, I thought the examples might have been a little thin, so I went ahead and I added some new examples and some new slides. If you've printed off the lectures that I had prepared originally, you'll see that some of the upcoming slides are new compared to those original slides. Let's do an example now. We have two sound sources. They're emitting sound in phase. Susie is 10 meters from one speaker and 8 meters from another speaker. We'd like to find the lowest frequencies for which Susie hears no sound and loud sound. Okay, so let's start by looking at our diagram. We've got two speakers. Let's call them 1 and 2. We know in these problems we have to worry about path difference, which means we need the distances to each speaker. D1 is the distance to the first speaker. I'm going to say that one's my 8 meters. D2 is my distance to the second speaker. I'm going to say that one is 10 meters. Okay, if we want to do the first part where she hears no sound, we know that that's destructive interference, and we know that our sources are in phase. Let's pick the correct equation. We have 4 of them written on the top. 1, 2, 3, 4. For this part of the problem, we have to pick in phase, so that's my top two equations, and then I have to pick destructive interference, so this is the equation we want to use for the first part. Delta D equals n lambda over 2, where n equals 1, 3, 5. Let's see what we're going to put in for our different bits and pieces of our problem. Delta D means path difference or path length difference. That's D2, take away D1. Doesn't matter which is bigger, so we take the absolute value. So our path difference is going to be 10 meters, subtract 8 meters, equals 2 meters. Okay, what about our wavelength lambda? Well, we don't know our wavelength, and we are trying to sort out frequency. We know wavelength and frequency are related because speed of sound is equal to v times f. That means lambda is v divided by f. We know that v means the speed of sound in air. We're not given a temperature, so we'll use v equals 344 meters per second. Okay, let's start to put these things together. Delta D equals n times lambda over 2, but lambda is v over f. And we're trying to solve for f, so f is equal to n times v over 2 delta D. Let's put our numbers in here. If we want the lowest frequency, then n has to be equal to 1. So we've got 1 times 344 meters per second divided by twice our path difference, which we already found was 2 meters, and that gives us a frequency of 86 hertz. Okay, that's the first part done. Next, we'll find the lowest frequency for which she hears the loud sound. To find the lowest frequency for which Susie hears loud sound, we have to identify our correct condition we're going to use. So loud sound. That means we want constructive interference, and we know the speakers are in phase. So now for our top 4 equations, we want the speakers in phase, and we want constructive interference. So that's our top equation. Delta D equals n times lambda, where n is equal to 0, 1, 2, and so on. We know that lambda is v over f, so we'll pop that in, which means f is equal to n times v over delta D. We know v is 344. We know delta D is 2 meters, so the last thing to pick is what is n. We know we want the lowest frequency. I think 0 is not a very sensible answer because a frequency of 0 isn't really a sound. Nothing is vibrating. So n equals the 1 is going to give us our lowest frequency. Let's put our numbers in. 1 times 344 divided by delta D, which we found was 2 meters, gives us a frequency of 172 hertz. So that's the lowest frequency for which Susie is going to hear loud sound. I'll leave as a homework problem for you to repeat the problem if we have sources that are out of phase. I won't make a video, but I will post the solutions. For this example, we have two sound sources and they're separated by 3 meters. That's drawn. We have Susie. She's standing 4 meters in front of one of the speakers. So there's Susie. The speakers are emitting sound out of phase. So one comes out on a crest and one on a trough. And the frequency is 688. Does Susie hear loud sound or no sound at all? It's asking about constructive or destructive interference. We know we're going to have to think about our conditions for interference. So I think our strategy here should be, let's find delta D. We know that's important for interference. Let's find lambda. That's important for interference. And let's see how what we get compares to our 4 equations for interference. Let's see which one matches. Whichever one matches is going to tell us what Susie hears. Okay, so there's our plan. Let's get started with delta D. We know delta D is the path length difference, D2 minus D1. Let's make sure we know what D1 and D2 are. D1 is our distance between Susie and speaker 1. That's given in our picture as 4 meters. D2, you might be tempted to write down D2 as 3 meters because 3 meters is given in the problem. But you have to remember D2 is your distance between Susie and speaker 2. Let's draw that on the diagram. You can see that that's the hypotenuse of a right angle triangle where the legs are 3 meters and 4 meters. So D2 is the square root of 3 meters squared plus 4 meters squared. That's equal to 5 meters. So then our path difference is 5 meters, take away 4 meters, gives us 1 meter. All right, wavelength is also important, so let's calculate our wavelength. We know V equals F lambda. That means lambda is V over F. We're not given any information to calculate V, so let's use V equals 344 meters per second. F is given as 688 hertz. So our lambda is 0.5 meters. Now we know it's the relationship between delta D and lambda that matters. So let's find the relationship between delta D and lambda. Delta D divided by lambda is 1 meter over 0.5 meters, which is equal to 2. That tells us that delta D equals 2 lambda. Okay, let's compare what we have here with our conditions for interference and see which one is the right match. Right off the bat, we know that our speakers are out of phase, so the equations we're looking at are the out of phase equations. If delta D is n times lambda over 2, or delta D equals 0.5 lambda, 1.5 lambda, 2.5 lambda, that matches constructive interference or loud sound. If delta D is 0 times lambda, or 1 times lambda, or 2 times lambda, that matches destructive or quiet. So it looks like what we found here matches destructive or quiet. We have delta D equals 2 lambda. Okay, so this matches destructive, quiet, the condition of which is delta D equals n lambda, and our specific case is n equals 2. Therefore, Susie doesn't hear any sound at all. Susie hears no sound. For a homework question, what if we turn the frequency up or down? What are the next higher and next lower frequencies for which Susie would also hear no sound? So what are the 2 closest frequencies for which Susie is not going to hear sound? So let's take that same example and let's put a slight twist on it. We've got our 2 speakers separated by 3 meters. Susie originally stood 4 meters in front of speaker 1. They emitted sound out of phase with a frequency of 688. Let's have Susie walk forward until she's standing right in front of speaker 1. What happens and what does she hear now? Let's remind ourselves of what happened in the original problem we did. We had delta D equals 1 meter. We had lambda was V over F was 0.5 meters. And we found that delta D was equal to 2 lambda, which matched our condition for destructive interference, which meant Susie heard quiet or no sound. Okay, what happens when Susie is right next to speaker 1? Let's follow the same strategy. Let's find delta D, which is D2 minus D1. Susie is right next to speaker 1. There's no distance between her and speaker 1, so D1 is 0. And she's 3 meters away from speaker 2, so D2 is equal to 3 meters. So our delta D is equal to 3 meters, subtract 0 meters. It's equal to 3 meters. Okay, this is a first interesting result for me. When Susie was far away, delta D was 1 meter. When Susie is close, delta D is 3 meters. So as a person walks in close towards the speaker, your path difference actually gets bigger. It's the biggest when you're the closest, and it's the smallest when you're the furthest away. As you walk away, your D1 gets closer and closer in length to D2. If you could walk infinitely far away, D1 would be equal to D2 and delta D would be 0. Okay, so let's compare delta D and lambda. Delta D over lambda is 3 meters divided by 0.5 meters equals 6. So delta D equals 6 times lambda. This matches our condition for when speakers are out of phase. We get destructive interference or quiet sound whenever delta D is equal to n lambda, and in this case, n equals 6. So when Susie walks in towards that speaker, she hears destructive sound or destructive interference or quiet sound. An interesting question might be what happened along the way, so why don't we do that on the next slide. Carrying on with our same setup, now we're asking what happened as Susie walked from 4 meters away until she stood right in front of the speaker. What did it sound like as she walked? So let's start with the 2 points we already know about. When Susie was 4 meters away, D1 equals 4 meters, we found that delta D equals 2 lambda, and that matched our condition for sources out of phase, destructive or quiet. So I'll put a quiet here. And when Susie was in right next to the speaker, we got delta D equals 6 lambda. That matched our condition for destructive, so she also heard quiet here. Well, what happened along the way? If we started at delta D equals 2 lambda, and we were headed towards delta D equals 6 lambda, then somewhere along the way, we must have passed through delta D equals 2.5 lambda. And then we must have hit delta D equals 3 lambda, delta D equals 3.5 lambda, delta D equals 4 lambda, delta D equals 4.5 lambda, delta D equals 5 lambda, and delta D equals 5.5 lambda. So we must have passed all those points as we went. We know that if it's an integer multiple of the wavelength and we're out of phase, that's destructive. If it's a half integer multiple for out of phase, that's loud. So as we walked through, at 2 lambda, we heard quiet. At 2.5 lambda, we hear loud. 3 lambda is quiet, 3.5 is loud, and so on. So as Susie walked, she heard a loud sound 1, 2, 3, 4 times. And she heard quiet sound 1, 2, 3, 4, 5 times.